All right, welcome everyone. I think it's time to get started. I punched in the recording already because we are at quarter past. We'll have a short break in about 25 minutes or so, and we'll have a short discussion then. First, we will go for a quick recap of what we did last time. So we're testing the expected value. That was the test. So the situation was as before, like with calculating the confidence intervals. Basically what we're doing is we're testing against the hypothesis. This time we put the confidence interval, if so to speak, around the null hypothesis, so that we have a null hypothesis assumption about the expected value. That's our null hypothesis. We put a confidence interval around that, and if our sample mean falls outside that confidence interval, then really the test rejects the null hypothesis. That's the basic idea. So why I taught the confidence intervals first, the confidence interval works a little bit differently. There we have the sample mean, and then that confidence interval moves around that. But in the hypothesis test, we have a hypothesized mean or hypothesized expected value, and then we put the confidence interval around that, and then we check whether our sample fell outside that scope. So in this case, the null hypothesis is rejected if we fall outside that interval. If it's a two-tailed test. If it's a one-tail test, we have a hypothesized expected value, and then we have a kind of like, we just have the other side. We consider that anything on that one side is meaningless, and if it's on this side but far enough away from the expected value, then we reject the null hypothesis again. So it's really important to understand the concept of the alternative hypothesis. If we're testing whether something is bigger, whether something is smaller, or whether something is different, and the hypothesis is kind of framed differently then. So here was an example. We calculated this annual rainfall, and we came to the conclusion that with a certain probability, I mean, we had like 1 point, I think we had about, I don't remember exactly what it was, but it was like four, I don't remember what it was now. I mean, we did that calculation last time, but a couple of percent. The p-value was about a couple of percent. So if we had this hypothesis test with, let's say, 5% margin of error, or alpha is 0.05, then we would reject the null hypothesis, and our alternative hypothesis is that the rainfall has diminished. So it's really important to understand, are we looking whether it's changed, whether it's grown, or whether it's becoming smaller? So it's a slightly different kind of a hypothesis then. We'll get to this. Like I said, the central limit theorem implies that for larger samples, the sample mean is approximately normally distributed, even if the original variable isn't. This means that we can use this for variables that are not normally distributed, provided that the sample size is large enough. So statisticians very often take the rule of thumb that if n is over 30, then it's normally distributed. I would hesitate to say this. I would not recommend in general clinging on to this kind of idea. What I do warn against is with a small n, we often see things like, I mean, if you look at, one thing that I know in particular, I've studied a little bit for my leisure time. I like sports, especially not sports as competitive sports, but sports as in human performance. And I myself like to do running and some strength training and so forth. So I read some of the publications regarding effects of certain nutritional choices, like, you know, if you eat a high carbohydrate versus low carbohydrate and so forth. And, you know, there's often this case where they check for performance differences. And they use this hypothesis testing, is it larger, is it smaller? But what they really do is they don't know, you don't notice it necessarily, but they're assuming that certain performance is like, it's a random variable and it's normally distributed, but it's not really normally distributed. You can't say that it's a normal distribution. If you take a running time of a 100-meter dash and claim that that's normally distributed, you'd have to have some data to back that up. And then they have n equals, let's say 5 or 10. You have two groups of people with 10 participants, and they calculate things like this statistical test they formulated, and then they even calculated with the t-test, which I will provide next. And it's ridiculous. If n is 5 or 10, this is all. It's just magical thinking that this is that the p-value means anything. What I'm just saying is that, yeah, it's suggestive if you have a smaller and larger and so forth. It's suggestive of an effect. But the analysis of whether the hypothesis is rejected or accepted, it's dubious at best if you have a small n. Now, when you have longitudinal studies with hundreds or thousands of people in them, then yeah, that's meaningful. But for these small scale tests, usually done on university students who are athletes or something like this, then there's no way that analysis is correct. So I'm just saying, even though you see this hypothesis test somewhere, try to understand how it works. What are the assumptions underlying it? And if someone tries to, I don't have a good, nice word for it. If someone tries to bullshit you by telling you, okay, we did this test and we have a, n equals 10, and we did this hypothesis test and we conclude that it's statistically significant, p equals 0.04, then it is very likely or possible that value is meaningless there. So just to be sure that you understand that if you have a small sample size, then the rejection or accepting or rejecting the null hypothesis is not necessarily very informative. Okay. The real issue here is the unknown variance. I mean, usually you don't know the variance. So the first question was when you know the variance and then you test whether something has changed. That could come in handy when you have a situation like the rainfall. But even then it's dubious because, we know something. I'm not an expert on climate science, for instance, but one thing we do know is that the models predict that climate change comes with often with increased uncertainty. That means that, that some people, like some experts say, that extreme events will become more common. That actually just means that the variance is actually increasing. So the rainfall example there, you might have periods where you have more extreme drought, and you may have periods when you have more extreme flooding. There's a huge amount of rainfall coming all at once and so forth. Have no idea whether this is actually happening but I'm just taking the word of certain experts on this. But in those cases, the test should not rely on the assumption that the variance is constant, that the variance is unchanged. So in this case, we would have to use sample variance as well. And one thing is that there lies, here's going to be some limits to what we can do with what we know now. So remember that when we have a normally distributed variable, but the variance is unknown, we can use the sample variance. But again, the normalized mean, you do have the hypothesized mean, the mu, and then you have the sample mean, the x bar, and you take x bar minus mu, then you have a variable with 0 expected value, and then you should divide it by it's a standard deviation, which would be sigma over square root of n, because the variance is sigma squared over n. But now you don't have the sigma. You have the sample variance, which is s squared over n, right? So you would have s squared over square root of n there. This replaces, I mean, this is exactly the same formula you'd have for the Z statistics. I like to talk about T statistic and Z statistic. The Z meaning that it's the normal distribution with known variance, and T knowing with using the sample variance. And now this T statistic follows the T distribution with n-1 degrees of freedom. And if we calculate this T statistic here, we should compare this to the critical value exactly like with the known variance, except that we're not using n01, we're using the T n-1 distribution, which for very large n will comport to the normal distribution, but with smaller n is far from it. Here's an example. A factory states that the diameter of a valve is normally distributed with 8.040 millimeter average. A new batch of valves is produced and 40 valves are examined. The average valve diameter is 8.038 and sample deviation is S is 0.006. A 5% chance of false rejection is acceptable. Should these valves be shipped? Meaning that, you know, the factory has stated that this is the average, 8.04, but we are 0.002 from that diameter on the average of 40 valves. Determine the p-value and discuss the effect of the high risk level on the probability of faulty parts. Okay, we'll stop the recording here and we'll have a short discussion about this together, also in groups. So here we are. I'm going to use this. So we have this normal distributed. So I'll use the null hypothesis. The mu zero is 8.040. That was the null hypothesis because this is the old normal distributed. We don't know what the variance is. We have a new batch, n equal 40 valves that are examined, and the sample mean x bar is 8.038. Sample deviation turns out to be S equals 0.006. Should the valves be shipped forward is the question. So, well, 5%, so we will use alpha equal to, well, here's the question. Which do we use? Well, it's the one-sided test, so we'll use alpha equal to 0.05. This means, in fact, that there is we are willing to tolerate a 5% chance, and I'm just using one-sided test, meaning that this looks like it's smaller, so we're going to be checking whether it's statistically significantly smaller. So we're going to be rejecting the null hypothesis if there's a 5% or less chance that this is outside of, you know, this is larger. Now, how do we calculate this? The statistics? We're going to be using the T statistic here. So I'm going to write this T as equal to, and I'm going to calculate it just like it stated it should. So we normalize this, so we get x bar minus mu zero divided by S over the square root of n. And now we get minus 2.1082. So we are going to be in the tail, the negative tail, meaning that we are on the small values part here. And I'm going to calculate the the p-value here, and we get it by calculating the T-inf. We're using the T-inf because this T is now the sorry, no. I'm frozen. My head is frozen. Just 1 second. I'm yeah. So we're going to have to calculate the TCDF. So the p-value comes from the cumulative distribution function, and then the threshold comes from the inverse of the cumulative distribution. Sorry, I froze for a little while there. Yeah. So we have that t value here, and our alpha is 0.05. Sorry, alpha is already this. Sorry, n minus 1. That's my. So we get p-value of 0.0207. And this is below the 0.05. So what do? We reject the null hypothesis. An alternative way would be to calculate the T alpha, and then we would calculate the T-inv of alpha and n minus 1, and we'd get minus 1.26849, and this would mean that because the t value is below this T alpha, then we reject the null hypothesis. Sorry, I froze there for a little while because sometimes you have to understand which way is which. So to calculate the p-value, you use the cumulative distribution function, and then to calculate the t value, or the threshold value for the t, then you use the T-inf of that alpha. Yeah.
Can I ask why we use the alpha and not alpha over 2?
Well, I'm using I could use alpha over 2. So what's the difference there? I'm using now alpha because I'm hypothesizing that if it has changed, it's become smaller, right? I'm using the one-sided test here. I could just as well calculate the t value wouldn't change, but I could calculate the t alpha at alpha over 2, right? And then I would get the upper and the lower value. Well, this would be just the negative of that. So I would get these two values if I used alpha over 2. So in the one-sided test, we are more willing to reject the null hypothesis because we're checking for, we kind of allow for the probability, for the contingency that it's actually larger. I mean, it doesn't really matter which test we use, but in this case, because it already looks smaller, so we're going to be using the one-sided test. But really, honestly, before the fact, we should really just stick to the alpha. 5% chance in both cases. I mean, in both cases, we are going to be rejecting the null hypothesis here, but you should really decide it beforehand. Usually when we are doing something for safety issue, for instance, then you usually use the one-sided test more readily if the other side is safe. I don't know if this means that, I don't even know if this is the case, because we are using, we're talking about valves, something, I don't know. Let's go back to the material now. I hope this answered your question. So I used the one-sided test here, and that's why I had this alpha, but I would use alpha over 2. I mean, it would be just as reasonable to use alpha over 2, because usually what we do when we use the alpha over 2, we usually do it before calculating this average. Now that we know that the average is below, then, has it gotten smaller? Yeah, it looks like that. Usually you can't do this completely without theory. Often you have to have some preconception or some theory. Like in the rainfall example, our question was, has the rainfall diminished? In this case, I asked, are these valves smaller than the previous ones? But it might just as well have been the question, are these valves different from the previous ones? And if this is different, the question is whether it's different, then we would use the alpha over 2, and we test look at it from both sides, right? So it depends on what you have formulated as your as your alternative hypothesis. Well, in both cases, luckily, in both cases, we conclude that these shouldn't be shipped forward because we got the t-value was below the threshold of both the alpha over 2 and the alpha. So it's either way. So what's the effect of the risk level on the probability of faulty parts? So if we increase the risk level here, so the 5%, if we increase the 5% to 10%, then what we're really doing is we're going to be more ready, easily rejecting the null hypothesis. And in this case, the null hypothesis is that it's still safe. So in fact, increasing the rejection probability will in fact keep us a little bit safer. You see, it depends on what the null hypothesis is, right? In this case, if it's dangerous for some reason to ship these faulty parts, then we might have a very low threshold for rejecting the null hypothesis. We would accept very little in terms of change there. But if we are trying to see if something has changed in the sense that we can make it, we have to draw new conclusions or something like this, then we shouldn't be very ready to reject the null hypothesis. So this is really it's really important to understand which direction your inference is going. In this case, if we are very much worried about quality control, we want the false rejection probability to increase, because then we want to minimize the probability of false acceptance. It really depends on what kind of deviation we are willing to tolerate here.
Sorry, can you again repeat the reasoning? For example, you got the p-value, and then did you compare it with the t?
Okay, I'll go back to the MATLAB window to explain. Just a second. Here. So what I did here, when I calculated this t-value now, this is like the normalized version. So if the expected value was mu and everything was normally distributed like we assumed, and the variance is the same as whatever it was before and so forth, then with this idea, we get a t-value, which this is the test statistic. We get a minus 2.108. And now when you calculate the p-value, this means what is the probability of getting a value such as this t-value or smaller if the expected value is still mu0. So if nothing has changed, we get this kind of batch 2 times out of 100 tests. So if we take 4,000 valves and split them randomly into groups of 40, so you get 100 groups randomly selected, then 2 out of those 100 groups will have this kind of this small average or smaller. Okay, so that is this particular patch is rarer than that 5%. So we conclude, because this is a 2% kind of batch, we conclude that it's not probably safe to ship out these valves under this process. You know, we have to go in and adjust the machine or check, make further checks or test something new. This doesn't appear to be within that 5% margin. So when I calculate this, there are two ways to conclude this. One is this p-value, which is now below that alpha, which is 0.05. Or the alternative would be to calculate the threshold value for that t, which would be minus 1.6849. And we conclude that this t value is below that threshold value, so we are rejecting the null hypothesis. Everything is not okay. Everything would be okay if it's above this. On the other hand, if we use the two-sided test with alpha over 2, then, you know, alpha over 2 would be 0.025. The p-value is still below that. But then we would also check for, I mean, it would be possible that this would be too big, and the p-value would be something like 0.9. In this case, the p-value, if it were the other way around, this would be too big by similar margin, then the p-value would be 0.99793, right? 1 minus that if it's too big, but the other way around. And then that, on the other hand, would be larger than 0.975, which would be the acceptability limit. Alternatively, if in this two-sided test we calculate the t-values for the 0.25 and 0.025 and 0.975 values, that would be the t alpha here and t alpha 2, then we would calculate, we would compare this t value here to these. This would be the interval, and it would still be outside this interval. It would be below this value. Alternatively, it could be above this value. I mean, if we had, let's x bar 2, it would be similarly larger. I mean, let's say it has the same sample deviation, but larger average. That would be 8.042, right? And if we calculate now, I'm going to calculate this T2 as equal to x bar 2. So it would be similarly largish value. And if we calculate this the p-value for this, let's call that P2, we have a similar result. It would be T2 n minus 1. So it would be above that 0.975. So this would be too large to fit in the within the 95% region around the hypothesized mean. So be that as it may, I mean, we have to reject this with the 5% risk factor. All right. I hope this answered your question.
Yes, sir.
Okay, good. I'll try my best to answer those questions, but it turns out that, honestly, it turns out often that this reasoning in the statistical tests is not always easy. It's not simple. All right. We can use the same test. Let's say that we have two variables, x and y, both normally distributed. Again, we assume normality here, but with large enough n, we can calculate their assume that they are use the same computation, assuming they are normally distributed if our sample sizes are large enough. So we have two groups. This is often the case when we study like the effect of a drug. We have x, a variable, you know, people who get cured if they are given a drug, and y, people who are given a drug and who are not given the drug and whether they are cured. Or some, let's say some performance outcome, X would be some nutritious pattern A, and Y would be some nutritious pattern B, so nutritional pattern. So for instance, we have X as people who, this X would be the 100-meter sprint time of people who eat low carbohydrate food, and Y would be the 100-meter sprint time for people who eat high carbohydrate food, or something like this. We have two samples from these. So we have, let's say we've taken these people, and we wish to determine if the outcomes are the same. So we take this as our null hypothesis, and we should assume that these, in this case, we assume that the expected values or the variances are known. We probably don't know the variances, but in this case, let's say that they are known. The nature of normal distribution allows us to conclude that x bar minus y bar should be normally distributed with the expected value of mu x minus mu y, and variance of sigma squared x over n plus sigma of y squared over m, where n and m are the sample sizes respectively. This hinges on the assumption that these two groups are, of course, these two variables are independent, and this is often a reasonable thing to make if we are talking about different individuals and so forth. So we have the test statistic, which we can formulate. We can just basically have the x bar minus y bar, and then we divide it by this square root of this joint variance. And this is a test statistic, and we can administer the test just as before. So as long as this is the thing you should understand. I mean, almost all statistical inference like this is based on doing a transformation on a couple of variables and in a way in which we get another variable whose distribution is known. In this case, it would be the N01 distribution if these variances are known and not calculated. And in this case, we can administer the test just like before. There's another possibility. It's that we assume that the variances are unknown, but we assume that they are equal. Then we can normalize the sample variances, combine them, and get an unbiased estimate of what the actual variance is. But this hinges on the idea that the variance is the same in both. So in this course and in this situation, sadly, we don't have a good test statistics for the sort of situation where the variances are both unknown and probably different. So that is something that we have to do separately. I'll explain that shortly, why that is. Well, okay, I'll explain that now. The reason is that in that situation, we cannot really formulate a well-known distribution in this situation. But if there are two possibilities. Variances are known. Both variances are known, in which case they can be different. Or two, the variances are unknown, but assumed that they are the same. See? Two possible situations. It gets more complicated, and we could, in theory, administer other tests then, but because this is just an introductory course, then I don't think there's a reason for us to go overboard in coming up with all these sorts of different tests. So we'll focus on this. So if the variances are the same but unknown, then we can calculate the joint sample variance, in which case we normalize this. So we have the divisor for this would be n minus 1 for this S of x. We multiply this first with n minus 1. Then we take this, the y, and we multiply this by m minus 1. So we get really the sum of the differences in those situations from the respective sample means. The x variable sample has a sum of differences of squares from the sample mean, and the sy has that same. So we're basically putting that sum above the line, and now we're dividing it by n minus 1 plus m minus 1. So it's n plus m minus 2. Oh, let's have a short break. I seem to have run out of paper here, so I'll write this in a better way. Just a few seconds. Firstly, we notice that Sx is basically the sum of I ranges from 1 to n x bar minus xi squared 1 over n minus 1. So we have S of x is defined like this. Sorry, S squared. Sorry. So this is the sample variance of x. And then the sample variance of y is, sorry about that noise, I'll mute that. 1 over m minus 1 times so we have that now. So if we look at this S squared in here, in effect, it's the sum so we do it like this. So it's simply the, when we have these, then we're basically calculating a similar average here. So we get a test statistic, and this S here, it works as our joint estimate of variance, and we get a T statistic here where we have a sample variance difference, sample mean differences divided by the normal, I'll just call it the normalized or combined sample variance there. And these test statistics have symmetric distributions, and the alternative hypothesis then of course depends on the particulars of the question. So for example, if we're testing whether a drug works, then we usually have a one-sided, an intervention works, we have a one-sided hypothesis, meaning that we expect it to be the same or better. Obviously, you know, for some drugs, that's not the case. Certain drugs that affect, for instance, the function of the heart may seem on a purely modeling perspective, it may look like, okay, this is probably going to be preventive of, let's say, cardiac arrest. But then when you administer it, it makes things worse. It could be. You never know. All right. But here's the test, and let's say we have these two variables, x and y. We have the same variance and same, same variance, and we have this two samples. The variance is unknown, but it's the same. And we have x as a sample size 1, 2, 3, 4, 5 samples, and y has 4 samples. And we have this hypothesis pair, null hypothesis that they are the same, and the alternative hypothesis is that they are different. use MATLAB. All right, we can do this, and you know, maybe I just do this here, show you how it's done. All right, so you see my MATLAB window now, right? So let's do it. So we have this, we first calculate x, this x sample of x. So I'm just going to use x. And we have 4.1, 4.2, 4.8, 4.6, and 4.9. This is my x. Y, 3.9, 5.1, 4.4, 4.2. Now, x bar, we can use the MATLAB function mean. It's actually used for that. Y bar is mean y, so we have these two. Now, how do we get the s's? So sx, we can write std of x, the standard deviation. It's the sample deviation there from x. Alternatively, we could calculate the variance of x and then take the square root of that, but it should be the same, right? The square root of the variance or the standard deviation, it doesn't really matter. So I'm going to use the s of x, and the same s of y is std of y. All right. Now we calculate the sample. We calculate the sample variance, the combined sample variance. So s is equal to, and look at the formula on page 193. So we get, okay, just before we do, I write, sorry, I forget what that was. The command for finding the length of a vector, I think it was size, yeah. So I have 5, so n equal 5, m equal 4. That was those were the sample sizes. So I'm going to calculate the sample variance, sample combined variance. So that's going to be, I'll put this upper part, the numerator in parentheses. So I have n minus 1 times s of x squared plus s2, but plus m minus 1 times s of y squared, and then I divide this by n plus m minus 2. So my sample variance is now 0.184. And I'm going to calculate the t-statistic now. So my t-statistic is going to be x bar, again, x bar minus y bar over the square root of, I have s2 over n plus s2 over m. That's my t-statistic. So we can probably already guess that it's definitely not going to be different, because my alpha is 0.05, and I can calculate the p-value of that t as TCDF of t, and I have here n plus m minus 2, right? And it's 0.6554. So it's well between 0. So my threshold for this p-value would be, it should be either below 0.025 or above 0.975, which in this case would mean that they would be either small, in the first case, it would be the smaller x's expected value would be smaller, and in the latter, y's expected value would be smaller. But we are well within that range between 0.025 and 0.975. Alternatively, we could calculate the interval at t inv of alpha over 2 with n plus m minus 2 and t inv of 1 minus alpha over 2 with degrees of freedom n plus m minus 2. And this would be our interval. And we see that this interval is pretty wide. So our t value is between those numbers. It's not on either side. So we don't reject the null hypothesis. We consider that it is null hypothesis stands so that there is no statistically significant difference between the samples of x and y. Right. I hope this was informative to you guys. So let's move back to the material. That was the example. Please be prepared to recreate this example and understand these numbers then. Well, in here we are testing equality of expected values. You know, either one is smaller or the other one is bigger, but you know, the null hypothesis being that the difference between the expected values is 0. And we had two cases. One, variance is known but could be different, and two, variance is the same but unknown. So how do we know if the variances are the same? Well, that's one thing we need to do. Let's say that let's just talk about first the test against previously known or assumed variance. We use here the chi-squared distribution. This is just like before when we calculated the confidence interval. Then again, we can do the same thing. We can think of this as calculating the confidence interval around the hypothesized variance, calculating the sample variance, and then seeing if it falls in that region. Alternatively, we can come up with the test statistic and see if the event that we're dealing with is a rare event. Either it's small, too small to be common enough to maintain the null hypothesis, or it's big, too big to accept the null hypothesis. Depending on what our alternative hypothesis is. There's a little bit of a misspelling here. That should be sigma squared, but so the null hypothesis, if the null hypothesis is the null hypothesis is always that this sigma squared is in fact what it was hypothesized to be, and if the alternative hypothesis that we test for is whether it's the variance has grown smaller, we have the critical region are the small values of our test variable. So if it falls into this small value test variable, then we conclude that yes, in fact, it is small. If it's big values, then it could be any of the very large values. I mean, this chi-squared distribution does stretch out to infinity, although the values, very big values are of course increasingly uncommon there. Alternatively, if we have that just to test whether they are different, so not smaller, bigger, but different, Then we have two critical regions, the small, very small values and the very large values. And then we reject the null hypothesis if it's either very small or very big. There's a bit of a typo here. That should be alpha over 2, in fact, and that should be alpha over 2. So that let me fix that. There's a typo there. That should be alpha over 2, and that should be alpha over 2. So just to understand that why that is, the total probability of the tails is alpha. So let's assume that we have a normally distributed variable. We have previously determined its variance to be 1,100. We take a sample to determine if the variance has changed. So again, let's use MATLAB here. So keep this page open and keep it in mind. I'm going to have to change the window a little bit so that I'm terribly sorry that all right, so I'll clear the command window here. So we have the sample given in there. So this needs a little bit of a typing to do. So the measured sample, measured values, and I'm using integers here because these are integers here, but really honestly, this already tells us that they're not from a normally distributed variable because they all can't be integers. So there's something fishy here, but we're just assuming that they are normally distributed. Otherwise, they should be just, you know, maybe they are rounded up or down. I don't know. 460, those are no commas needed. 460, 351, 421, 339, 439, 402, 422, 470, 310, 416. Okay, that's now my sample. And now I'm going to calculate the S, which is the STD of X, right? I mean, we could calculate the S2, which is the variance of X as well. It's about 2,700 something. Seems really big, rather big. Our alpha is 0.01. So we calculate the critical region and we can calculate this from, well, I forgot. So N is 11. So we calculate the critical region of this first. So let's calculate the critical region first. And we're using chi-squared distribution. So it's and we have alpha over 2, and our degrees of freedom is n minus 1. And so we get this critical region, which is this. But now we have to calculate the W statistic or the chi-squared statistic, which would be our perpetuate sigma squared should be 1,100, right? Now we calculate the test statistic W, which is n minus 1 times S2, which was the sample divided by sigma 2. What did I forgot the. So we get 25.1007. And now this is not in the critical region. I mean, remember the critical region is those values below 2.1559 and above 25.1882. So let's calculate the p value for this. So the p-value for this, you know, we already know this is going to be in the high end. So we're calculating the p-value at 2 times 1 minus W, and that would be at n minus 1. Our p-value is 0.01303. So it's very, very, very close to being significant. But we remember we wanted the p-value, the threshold at alpha equal 0.01. So we will have to maintain our null hypothesis at significance level alpha at 0.01. It's awfully big, the variance here, and we are all but ready to conclude that it's actually too big. But honestly, we chose alpha to be 0.01, and here we are. So it is in the allowed interval. Our test statistic is in the allowed interval. So this is a very close case, but no, it's not significant in this case. Not with alpha equals 0.01. If we had alpha equal to 0.05, then we would reject the null hypothesis. So really, I mean, it's all about the p-value and what do we do with it. Often, nowadays, it's usually when you see people reporting statistical analysis and inference, that they calculate the p-value, and then if the p-value is something like this, then they say that they use some people, in some subcultures and some sciences, people use different kind of languages. Sometimes they say if it's 0.05 below that, then it's somewhat significant, and if it's below 0.01, it's significant, and if it's below 0.001, then it's very significant, or something like this. People may say something like this with their, but really it's up to you to determine what to do with this. I mean, the inference here should be that, yeah, well, if the variance is what it's supposed to be, then this kind of sample of 11 points, it has about just over 1% chance to emerge something like this with this big or larger sample variance. So this is not that common, but it is possible. It is plausible that this is from the original. Right.
So did we conclude that the variance did not change?
We conclude that if the required significance level is 0.01, so sorry, yeah, if the required significance level is 0.01, we conclude that the variance, it isn't that much different. But I mean, the point here is to understand that we got actually a pretty big variance here, and it's very close to the threshold, but it's just below it. So if we cannot tolerate a fall and you know, a type 2 error, or sorry, type 1 error of chance of you know, bigger than 0.01, then we cannot conclude that the null hypothesis is rejected. It's really, it's to the risk, it's because the alpha was determined to be 0.01. So I'm going to move back to the material. So here, in this example, if our alpha would be larger, even by a little bit, it would be 0.01, then we would say that, yeah, the variance has changed. But with alpha equal to 0.01, we conclude that no, it hasn't changed. Not that much, at least. So really, it all depends on what we choose as the significant level. This is my take here. So in many fields, people teach, I mean, very often the cases where people teach that this 5% or 0.01 significance is somehow, it's commonly used, but it's in no, not in, there's nothing physical or mathematical to justify why it should be that. In fact, there is a story which I probably don't remember correctly, but if I do, I don't remember the names of the people. I'm really bad with names, but it has been claimed that this significance level comes from a bet or a wager. They didn't call it bet, they call it wager, by some English gentlemen in high society somewhere in the 19th century. So again, this goes on record, so this is something I heard and I don't probably remember it correctly, so drop a line at the comments if you find that there is something wrong or some inaccuracy, or if you remember the source of this story, because I don't. So this there was this gentleman who had a tea party. People, people drink tea in his house, at his house. And then the maid or some person, the kitchen helper, would pour some milk into the tea. English being the barbarians that they are, that they put milk in their tea. And one of the guests said that they can taste the difference of whether the milk was poured into the cup first and then the tea was poured on top of that, or whether the tea was poured in first and then the milk on top of the tea. And then they had a debate. How do we determine if she can actually if she can actually taste the difference? Well, what they would do is that they would have an equal number of cups filled with tea and milk, and one group of these cups would be filled one way and the other group of cups would be filled in another way. And then they would be shuffled and only the maid would know which one would be which. And then they calculated and okay, they knew the binomial distributions and so forth. And they calculated what would be the situation where we believe this lady that they are in fact able to recognize, and how many cups they would need so that they would fully recognize those cups. And they determined that they make the test in such a way that if the chance of getting it correct by pure chance is less than 5%, less than 1 in 20, then they would conclude that yes, she can actually taste the difference. And I'm not sure if this is the reason for the 20% or not 20%, the 5% or the 1 in 20 alpha that is often used, but it's a nice story. So, but comment if you know that this is wrong or if you know the source of this story, because this is what I've heard and I'm not sure of the source. All right, let's continue. There was a hypothesized thing earlier where we said that you can test the hypothesis of equality of these expected values if one of the two things holds. One, that you know the variances. Well, you usually don't know the variances, in which case they can be different. Or you don't know the variances, but you should be able to assume that they are the same. So one way to do this, to see whether this assumption, I mean, you cannot enforce this assumption, but what you can do is you can test first for this assumption, and if that assumption holds, then, if you test it and the null hypothesis remains, then, you can maintain that, okay, these are, for all intents and purposes, these variances are the same, so we're going to be using that assumption. So we can also administer a test whether the variances are equal. And this is the last distribution that is different from what we've had. This is the last new distribution. I'm not going to go into the specifics of this. It involves heavily the application of the gamma functions and so forth. So we're not going to be learning what it is. We're just going to be using software to invoke this distribution. So this is called the F distribution, also known as the Fisher distribution. Sometimes call it Schneideker distribution. I don't even know how to pronounce that, but we just call it F distribution. And where does that F distribution come from? The F distribution can be obtained by calculating a quotient of two chi-squared distributed variables. The distribution has the symmetry that if you switch the roles of the parameters n1 and n2, then you gain a symmetry around, a multiplicative symmetry around the value 1. So F is distributed with n1, n2, if one and only if 1 over F is distributed with n2 with parameters n2, n1. So it has the consequence that the probabilities have this inverse relationship, so that probability that this F variable is smaller than or equal to F is the same that 1 over F is larger than or equal to 1 over X. This shouldn't, there's something wrong with this. Just disregard that. That should be always true, but I mean, I'll just disregard that. I'll fix that. Oh, why did it do it like this? I just draw it like this. Disregard that anyways. This one you can disregard. Why is it moving that? I'm not going to use that anyways. The point here is this. We calculate the F statistic by calculating quotient of two chi-squared distributed variables that are normalized by dividing with their degrees of freedom. And the thing is, if we have two samples of normally distributed variables, then their sample variances divided by their actual variances, then the quotient is going to be F distributed with n-1 and m-1. So this is fairly easy to prove by noticing the chi-squared distributed nature of these test variables that we came up with before, with the change of the variance, whether the variance is in the hypothesized region. And in particular situation where these variances are the same, we actually can eliminate everything else here except the sample variances. So the F statistic is notoriously easy to calculate. You just calculate the quotient of the sample variances. When you calculate the quotient of, the quotient of one sample variance divided by another, just make sure that you have the N and M in right places, then you have the F statistic. And in this case, you can calculate the F values and the probabilities of the P values using F and F in. I'll have to check out what the command is in MATLAB. I don't remember it, but let's see if I can find it. And this gives us the test, basically the test variable F you get, and then you can use the F distribution to come up with this. So we'll have to check. I thought that we wouldn't get this far actually in this lecture, so I didn't hone my memory of what the F distributions command is in MATLAB. We still have about 5 minutes time, so let's go there. I'm not going to, I don't remember it now. I was going to check it for next time, but let's see. So we would need the F distribution. I wonder, was it FCDF? Yes, and Finv, is it? Yeah, it seems to be. So yeah, it's just FCDF and Finv. Okay, that's cool. So please take a look at the slides. So here we have, the course has 51 students and the number of points and blah, blah, blah. We have N as equal to, so NA, the first course has 51 students. We have gathered the sample and we get S2A at equal to 478, the sample variance there. Another course, NB, maybe the Finnish, maybe that's the English version of this course and maybe this is the Finnish version of this course, I don't know. Has the same exam, 26 students, and S2B is 372. Is it reasonable to assume that the variances are different? So we calculate the F statistic, and we can take the F statistic as simply S2A over S2B. Now. And now we can calculate the p-value basically from this. So we can calculate the FCDF of F, and remember here we have to make sure, you know, the numerator was that A, so we have NA, and the denominator was NB. And we get that this is 75%. So we conclude that it's not reasonable to assume that they are different because the F statistic is between, it's between the the p-value for the p-value is above any reasonable, so the p-value is any above and below reasonable limits. So usually the limits would be 0. If we have 5%, if we have the 0.05 alpha, then it would be 0.025 and 0.975 at the limits, and this is between those. Alternatively, we could come up with the critical regions, lower and upper limits, and that would be F in the below, and here we would have the p-value would be 0.0225. Assuming that we're using the 5%. Again, if we're using 1%, it would be something different. If we're using 10%, doesn't matter. And here we would have NA, NB. Oh, actually, this should be NA minus 1. Sorry, I made the blunder here. Those would be, yeah, it should be NA minus 1 and NA and B minus 1. So I'll have to recalculate the p-value. The F statistic itself is correct, but the p-value needs to be calculated different. And then upper limit would be F in of, and we would have 0.975, NA minus 1, and B minus 1. The critical region would be somewhere in there, 0. So my F value is definitely not outside the critical region, outside the acceptable. This is the acceptable region. Basically anything below the lower value or above the higher value would be in the critical region, right? So I'll recalculate the p-value because I actually did that wrong. It should be n minus 1 here and minus 1 here. Doesn't change it all that much. It's, if anything, it's even more conservative, this value, right? So this was actually it. This was the last new thing in this course. So we're now done with everything in the lecture slides. And this was the last test. So on Thursday, we will go through the testing chapter, one by one. And I'll also do some recap of other things. We'll look at some of the examples. Next week, we still have the lectures and exercises, I think, yeah. And that will be the last week, next week. And during that week, I will go through the highlights of this course and we'll go through some of the examples. I'll show you some of the example material that has been published now, and we'll do some MATLAB exercises here. So you have now, basically, I have now gone through in this all the material that is going to be needed in the exam. It's this test, yeah?
So the variances are not different. That was our
Yes,
conclusion.
yes. The result was that the variances are not different. Yeah, here. Yeah, that's true. I'm now going to stop the recording, and this is I'll still, before I do stop it, I'll just say it on record that I will record next lecture, but that will be the last recorded lecture probably, right?